Welcome to the AI Checkpoints.
Before we begin this deep dive, just a quick reminder. This content is generated by AI. Our focus is on summarizing and analyzing the source material for you.
Okay, so let's unpack this fantastic playbook we've got today. We're diving into the strategy from some real heavyweights, Kaggle Grandmasters, Kazuki Onodera, Theophile, Gilberto Treiteritz, and Chris Diot. They laid out their 7 battle-tested modeling techniques for tabular data.
Yeah, and this isn't just, a random collection of tricks. It's really presented as a repeatable system, something they've honed over hundreds of competitions for solving real-world tabular problems and doing it fast.
Right.
And the core theme that keeps coming up is how GPU acceleration makes these pretty advanced techniques actually practical when you're dealing with large data sets.
So our mission for you, the listener, is to pull out that core foundation, the stuff you can't skip, and then really get into those 7 specific techniques that these folks use to consistently hit the top of the leaderboards.
Exactly. And it starts, maybe surprisingly, not with some complex algorithm, but with discipline. The authors really hammer home that 2 principles are the engine for their whole playbook.
Oh, okay.
Get these wrong, and you're basically just guessing. Those
Yeah.
are fast experimentation and careful validation.
All right, let's take fast experimentation first. Why is speed specifically such a big lever here? I mean, faster is always better, but why is it fundamental for them?
Well, it's because the more high-quality experiments you can run, the better your chances. More experiments mean you explore more features, try more models, tune more parameters.
You find more patterns.
You find more patterns, exactly.
Okay.
And just as importantly, you catch models that are overfitting or, just failing badly, much faster. But the key insight is optimizing speed across the entire pipeline, not just the training part.
Okay, so not just waiting for the model to train faster, but the whole process.
Precisely. This means speeding up the data handling itself. They talk about using GPU drop-in replacements for things like pandas or polars, specifically mentioning NVIDIA cuDF.
Right, cuPD.
So your data frame operations, loading, cleaning, filtering, and especially complex feature engineering, which will get to happen way faster. Minutes, not hours.
That makes a huge difference for iteration, doesn't it? If data prep takes hours, you might only try one big idea a day.
Exactly. If it takes minutes, you can try dozens. And then, yes, that speed carries over into model training with tools like NVIDIA cuML, or just using the GPU versions of XGBoost, LightGBM, CatBoost, the ones many people already use.
So without that GPU speed up, some of the later techniques are just theoretical.
Pretty much.
Yeah.
Especially things requiring retraining multiple times. They become impractical on big data sets within, say, a competition deadline or even a normal project timeline.
Okay, so speed is pillar 1. Pillar 2 is careful validation, or CV. You said if you can't trust your local score, you're sunk.
Absolutely. Cross-validation is the bedrock. Because if your local score doesn't reflect how the model will actually perform on unseen data, then all your effort optimizing that score is wasted, maybe worse than wasted.
And they use k-fold CV, rotating through the data.
Yeah, the standard k-fold approach. It ensures every part of your data is used for validation exactly once, giving you a more reliable performance estimate than a single train test split.
But they add a really important warning here, which I think trips people up a lot. Matching your CV strategy to the test data structure.
Yes, this is crucial. It's about simulating the real-world scenario. If your data has a time element, like predicting future sales, you absolutely must use something like time series split.
To avoid peeking into the future. Right?
Correct. You can't let your model train on data from Tuesday to predict Monday. And similarly, if your data is grouped maybe by user or patient or store.
Like all records for user A should stay together.
Exactly. You need group k-fold. Because otherwise the model might train on some of user A's data and then get validated on other data from user A. It learns user-specific quirks, looks great in validation.
And then fails miserably when it sees a brand new user.
Precisely. Mismatched CV is a fast path to deployment disaster. They make that very clear.
Okay, foundation laid, speed and careful validation. Now for technique 1, smarter EVA. Going beyond the basics, what are these critical checks they add?
Right, so everyone checks for missing values, maybe outliers. But the Grandmasters add 2 really vital checks. First, train versus test distribution checks.
Looking for distribution shift.
Yes. Actively checking if the data you're evaluating on looks statistically different from the data you trained on. This happens all the time in the real world.
Like the data collection changed, or the test set is from a different time period.
Exactly. And if you don't spot this shift, your model might seem great locally, but be totally useless in production. They point to the Amazon KDD Cup 23 winners, who apparently had to completely rethink their approach after finding this kind of shift.
Wow. Okay, that makes the second check pretty critical too, analyzing the target variable for temporal pattern.
It really is.
Yeah.
You need to plot your target variable over time. Look for trends, seasonality, sudden jumps, things that might fool a model if it's not time aware.
Like that classic example of predicting ice cream sales without accounting for summer.
Sort of, yeah. Or maybe a more subtle weekly pattern.
Mm.
If you ignore it and your validation isn't time aware, you're misleading yourself.
Mm.
And again, doing these deep checks on millions of rows, that's where the GPU acceleration with cuDF becomes essential, just to get it done quickly.
Okay, technique 2. Building diverse baselines fast. Why not just build one simple baseline? Why spin up several different types of models right away?
Because a single baseline gives you just one narrow view. They want a quick, multi-angled gut check on the data's landscape. So they'll fire up a linear model, a couple of GBDTs, maybe a small neural net, all at once.
What does that tell them?
Several things. It sets a clear performance floor. You have to beat these. It helps confirm later that your complex feature engineering is actually adding value. And crucially, it's a great way to spot problems early.
Like data leakage.
Exactly. If your simple linear model suddenly gets a near-perfect score, something's wrong. You've probably leaked information from the target into the features. Diverse baselines help catch that fast.
And they had an example where this paid off big time.
They did. In a rainfall prediction competition, their initial baselines, an ensemble of GBDTs, NNs, and support vector regression, were actually strong enough on their own to get second place. Didn't even need super complex features initially.
Just the baseline ensemble was that good.
Yeah, and they noted even a single support vector classifier did surprisingly well. This rapid baseline approach only really works because GPU acceleration, like using cuML and fast GBDT, lets you train these varied models in minutes, not hours or days.
Okay, now we're getting into the serious performance boosters. Technique 3, feature engineering. With powerful models like GBDTs, why is manually creating potentially thousands of features still such a dominant strategy on tabular data?
Because even smart models often can't see complex interactions or incorporate domain knowledge unless you spell it out for them through features. Raw data is rarely in the perfect format.
And they're not talking about adding just 5 or 10 features.
No. The scale is key. They emphasize going broad, generating hundreds, maybe thousands of features, often by combining existing ones, especially categorical columns.
Combining categories, how does that work?
Say you have 8 categorical columns, you could try combining every pair. That alone creates 28 new interaction features. They mentioned this approach was key to winning first place in a couple of Kaggle competitions.
But generating and testing thousands of features sounds like it would take forever.
It would, traditionally. That's where the GPU acceleration for data manipulation comes back in. Using cuDF for these kinds of large-scale pandas-like operations means you can generate and test these vast feature sets in maybe days, instead of what could literally take months otherwise.
Right, makes sense. Okay, technique 4. Hill climbing for ensembling. This isn't just averaging model prediction.
No, it's smarter than a simple average. Hill climbing is an automated search for the best weighted average. You start with your single best model. Then you iteratively add predictions from your other models, one by one.
How do you add them?
You test different weights, say 90% of Model A and 10% of Model B. Does that improve your validation score? Okay, try a D20. Find the best blend for A and B. Then you lock that blend and try adding Model C with different weights, like 95% of the A plus B blend and 5% of C.
So you're always climbing towards a better validation score by tweaking the weights.
Exactly. It finds a blend that specifically leverages the complementary strengths, where one model zigs, the other zags. They mentioned this secured first place in a predict calorie expenditure competition.
But testing all those weight combinations must be computationally intensive.
Hugely. That's why they use CuPy on GPUs. It lets them vectorize the metric calculations, like RMSE or AUC, and evaluate thousands of potential weight combinations in parallel really fast. Makes large-scale hill climbing feasible.
Okay, then technique 5, stacking. This takes ensembling even further, right? It's like another layer.
Yeah, stacking is often seen as the big gun of ensembling. You basically train a new model, a stage 2 model, often called a meta-learner, whose only job is to learn the best way to combine the predictions from your first layer of models, the stage 1 base models.
So the inputs to the stage 2 model are the outputs of the stage 1 models.
That's precisely. But you have to be careful about leakage here. The key is to use out-of-fold, or OOF, predictions from stage 1 as features for stage 2.
Explain OOF again quickly.
When you do k-fold cross-validation, each model is trained on, say, k1 folds and validates on the one held-out fold. The OOF predictions are the predictions made on that held-out fold. So the stage 2 model learns from predictions made on data that the corresponding stage 1 model never saw during its training.
Ah, okay, that keeps it clean.
Yes. They also suggest maybe feeding the residuals, basically. The errors made by the stage 1 models into the stage 2 model as well. Helps it focus on fixing the mistakes. Stacking was apparently key to winning a podcast listening time competition using a complex 3-level stack.
And computationally.
Very demanding. Training multiple base models, generating OOFs, then training a meta learner. It adds up. Again, EUML and GPU-accelerated GPDTs are pretty much essential to make deep stacking practical.
All right, moving towards maximizing data. Technique 6, pseudo-labeling. This sounds intriguing, using your model to label unlabeled data.
It is intriguing and powerful, but also needs care. The idea is you take your best current model, often your stacked ensemble, and use it to predict labels on unlabeled data, maybe the test set itself or other available data.
And then you add those predictions back into the training set.
Essentially, yes. You fold these pseudo-labels back in. Ideally, you use soft labels that predicted probabilities rather than forcing a hard 0-1. This acts a bit like knowledge distillation and can really boost model robustness and help it generalize, especially if the unlabeled data covers slightly different territory.
But the risk seems high. Couldn't the model just reinforce its own mistakes?
Absolutely, that's the main danger. And leakage is critical here. If you're using k-fold CV, you must generate k different sets of pseudo-labels. For fold 1's training, you only use pseudo-labels generated by models trained on folds 2 through k. You never let a fold see pseudo-labels generated by a model that was trained on its own data.
That sounds complex to manage.
It requires careful bookkeeping, yes, but it's the only way to prevent the model from getting overconfident based on its own potentially flawed predictions. They mentioned using this in the Bird CLE 2024 audio classification task to help generalize across different bird calls and recording conditions. Again, the speed matters because you're effectively retraining multiple times.
Okay, final technique, technique 7. Strengthening your final model with extra training. What are these last tweaks to squeeze out performance?
These are relatively simple steps to maximize what you've already built. First, train the same final model multiple times using different random seeds, and then average their predictions.
Why does changing the seed help?
Small changes in initialization or data shuffling order can lead the model down slightly different optimization paths. Averaging these slightly different models makes the final prediction more robust, less sensitive to any single random initialization.
And with fast GPUs, training the same model 10 or 20 times isn't a huge burden anymore.
Exactly. They saw a clear benefit in a fertilizer prediction challenge by ensembling XGBoost models across 100 different seeds. The second step is even simpler. Once you've nailed down your best model architecture and hyperparameters through careful cross-validation,
Yes.
retrain that final model one last time on 100% of the available data train and validation combined. You've used the CV to find the best settings. Now you use all the data to give the model the best possible final representation before deploying it. So if we kind of tie it all together, this whole playbook from the Grandmasters, it really rests on those two foundations we started with. The ability to iterate incredibly fast and the discipline to validate meticulously.
Right. Those enable everything else.
They do. They make it possible to actually implement these 7 advanced techniques. The smarter EDA, diverse baselines, massive feature engineering, hill climbing, stacking, pseudo-labeling, and the final training tweaks which collectively drive that top-tier performance.
So for you, the listener, what's the big takeaway here? It seems like achieving state-of-the-art results on tabular data is maybe less about finding some magical new algorithm.
Yeah, much less.
And much more about adopting this kind of disciplined, systematic, and accelerated workflow. The ability to generate and test thousands of features, build complex ensembles. It really hinges on having the computational power, largely from GPUs using tools like cuDF and cuML, to make it practical.
Which leads to, I think, a really important question for you to reflect on. Before you chase the next hot model architecture, maybe ask, how much is your current process holding you back? Is it leaky validation? Or is it simply that your iteration speed is too slow to explore ideas thoroughly?
That's a great point to consider. How much performance is being left on the table just due to workflow friction? Hit like and subscribe if you like the content. See you next time.